now I don't know whether to repeat what I just said. So what I just said is still true. So what we're going to do today is we're going to start adding back in behavior that is associated with the fact that light is actually a wave, that there are things wiggling. We're not going to put everything back in. Tomorrow we'll talk about interference. But the feature that we're going to add in today is essentially a discussion about directionality, and that is, if we're just talking about the propagation vector k, then that sets a special direction in space. It's the direction in which the wave is moving. Okay, then we can also say, well, the electric field, let's just pick on the electric field, for example. The electric field has to be wiggling in some direction that is orthogonal to the k direction, because all three of these things have to be orthogonal, k, e, and b. So the direction in which the E field is oscillating also picks a special direction in space. So for example, if the k, it's easier to draw this with the k vector coming out of the board. If the k vector is coming out of the board, the directions transverse to that are in this plane, the plane of the board. And a priori, the electric field could be oscillating in any direction in that plane. And our discussion so far hasn't really cared in what direction the electric field oscillates, but today we actually want to look at phenomena that are based on the fact that when the electric field oscillates, it picks out another special direction. Say in this example, maybe it's oscillating up or down. Okay. So the direction in which the electric field oscillates is what we call the polarization direction of the wave. We could just as well talk about the direction in which the magnetic field oscillates, because if we know how any two of these vectors point, we automatically know the third, because the electric, magnetic, and propagation vectors are all mutually orthogonal. But by convention, when we refer to polarization, we're talking about the electric field. So that's what we'll always have in mind when we talk about the polarization direction of a wave. Now, one important aspect of polarization to keep in mind is that when I draw the polarization, I really shouldn't think of it so much as an arrow. Because remember, the electric field is oscillating. It's going up, and later it's going down. Okay? So for example, if I took this polarization direction pointing up, at some later time it will point down. So saying that the polarization of the electric field is up is really only something I could say at an instant of time. What we typically refer to as the non-directed polarization axis. What that means is that if I rotate the polarization of a wave by 180 degrees, I haven't really changed anything. Okay. All right. Now, before I actually get started talking about polarization and types of polarization and how we manipulate polarization, I'm going to take a pause for just a moment and discuss one particular example of generating electromagnetic radiation, which is going to turn out to be pretty useful in our discussion a little later on. So we talked about a lot of light sources last time. We said you can heat things up and get incandescent light out. It's very sloppy. It's got this continuous distribution of intensity as a function of frequency. It's very non-directional, yada, yada, yada. We talked about gas discharge tube scenarios. We talked about fluorescence. We eventually talked about lasers, and we put one together. But there's actually another way to create an electromagnetic wave, which I would argue you have a lot of control over. Okay? And we do have a lot of control over lasers, and they have properties that we really like. But there's another scenario where you can generate electromagnetic radiation with a pretty fine control over, for example, the direction in which things are oscillating, at some level of the phase. Does anybody know how you might go about generating electromagnetic radiation where you have like knobs you can control to govern the properties? So what do you need to get light? What is light made of?
Changing electric field.
Oscillating electric and magnetic field. So if you could somehow create an oscillating electric field, then by Maxwell's equations, that will act as the source for an oscillating magnetic field, and then they will happily travel off together. So what's the simplest way to create an oscillating electric field? Well, you can spin things, but another way is to just wiggle charges back and forth, up and down. Okay. So we now have in mind one of our simplest means of generating electromagnetic radiation is to take a wire, or what we'd like to call an antenna, and just drive an AC current back and forth along this wire. Okay? If we think of that as just charge distributions moving back and forth along the wire, then this itself creates an electric field, which is oscillating back and forth along the wire, the same frequency as our driving frequency. And that time-varying oscillating electric field will create a time-varying magnetic field, and then those two things can source each other and move away from the original antenna source of this electromagnetic wave. Okay, so this is a linear antenna acting as a transmitter. Okay, it's creating the wave. So this thing you have to plug into the wall. So here, we'll plug it into the wall. I like to plug things into the wall. So it's on. Okay, so now what I want to talk about for a moment is the kind of radiation we get out of this. Okay, we can clearly control the frequency, but let's talk about the direction in which this radiation comes off. So if my electric field is oscillating up and down, then if I think about this picture right here, I can imagine that traveling off in, say, this direction, and then I would just have that electric field oscillation like so. The magnetic field would be transverse to that, and I would have this nice electromagnetic wave moving off. But let's ask if we can get radiation in any other directions. So for example, is it possible to have the radiation from this antenna move off in this direction? Why not?
E and K are parallel.
Yeah, if the electric field I'm inducing is parallel to the axis, K can't be parallel to the axis because then E and K would be parallel, and you can't have that for electromagnetic radiation. They have to be perpendicular. Okay? So the effect here is that we see zero emission along the axis of the antenna. What about in some other direction, maybe like that? Could I have radiation moving off at an angle that's not 90 degrees from the axis of the antenna? Argue for it.
I think it would just be lesser.
It would be lesser? By how much?
Cosine theta.
Yeah, so what we have in mind is that the electric field vector, which is this way, can be decomposed into a piece which is perpendicular to the K vector and a piece which is along the K vector, and of course the piece along the K vector doesn't contribute to electromagnetic radiation. But as long as there's some component perpendicular to the K vector, then that can comprise the electric part of electromagnetic radiation leaving the antenna. So in the end, if we take a linear antenna and we drive it with an alternating current, what we find is a dipole radiation pattern, which we usually exhibit in terms of this lobe structure, where this is actually revolved around the axis of the antenna. And the idea here is that the further away the lobe is from the antenna axis, the larger the intensity in that particular direction, with the largest intensity moving off in directions perpendicular to the axis of the antenna. Okay? So, any questions about dipole radiation? Okay, we're going to come back and find this to be a useful thing to recall in just a few minutes, but for now let's jump on to our discussion of polarization. So, when we talk about polarization, again, the degrees of freedom that we have in mind are constrained to live in a plane. So we're essentially picking a direction in a plane. Now, if we have a plane, and that's two-dimensional, right? So if we want to describe directions in 2 dimensions, one simple way to do it is just to set up some coordinate axes, x and y, and express directions as things having x components and y components. Okay? Of course, we could pick any x and y we want. All of them are just as good as any other. Okay? But it's going to turn out that there's another way of describing directions in this plane, which you've probably never seen before, but we will actually find it to be quite useful when we talk about certain states of polarization. And that is, instead of x and y, we'll think of it as clockwise and counterclockwise. So we'll encounter why clockwise and counterclockwise gets useful a little later in the morning. But for now, let's talk about some of the states of polarization that we tend to work with. So what I'm going to do now is list what I like to think of as special polarization states. These are polarization states which are mathematically straightforward to describe. They're not they don't use really crazy functions. And they have really nice properties. They're good to use in experiments. You can predict more or less what they're going to do. In general, a sloppy state of polarization is none of these, and it's mathematically very hard to describe. And it's hard to predict what it's going to do. So it's kind of like geometries, right? A sphere is a really simple geometry. You are not a simple geometry. It's very hard to figure out what will happen to you if we do physics with you. So what are the special polarization states that we tend to encounter? Well, first of all, it probably comes as no surprise that the simplest and most intuitive is a state of linearly polarized light. And the reason I say this is the most intuitive is because if I say think of a wave, some of your initial ideas are probably water waves, wave on a string, maybe electromagnetic waves. We don't see those very often in the way that we like to visualize them as oscillations. But water waves and waves on strings typically exhibit linear polarization. And what that means is, if we think of it classically, it just means that the entire wave is wiggling along one line. So maybe up and down. Okay. In fact, at this point, it might be hard to imagine any other kind of polarization for a wave, but we'll see some other possibilities. Quantum mechanically, and today it's going to be useful to recall at certain points that light is actually comprised of these little things called photons. Quantum mechanically, we don't have one big wave. That's the classical solution to Maxwell's equations. Quantum mechanically, we have a lot of photons, and each photon has a polarization direction. Now, the polarization of a photon is a funnier concept because we don't tend to think of a photon as a wave itself, but it still has a polarization direction on degree of freedom. And so, in the quantum mechanical version of linearly polarized light, what we find is that we have a collection of photons, and their polarization directions are all lined up with each other. So that if I just added up all of the polarizations of this collection of photons, I get the net linear polarization of the classical wave. So, what other kinds of polarization are we going to encounter? Well, another kind of polarization, which is kind of an unkind of polarization, is unpolarized light. Light that is not polarized. Now, in the classical version, I don't really have a good way to visualize unpolarized light. Classically, unpolarized light is kind of hard to visualize. However, in the quantum picture, we have a nice way to view what unpolarized light is, and that is essentially to say that it is a perfectly random distribution of individual photon polarization directions. So that is, I take a large collection, or what we call in quantum mechanics an ensemble, of photons, and they have perfectly random polarization directions, so that on average, for any one photon with a given polarization, there's always another photon whose polarization is at 90 degrees to it. Okay, so I mean, I'm not going to draw a whole bunch of photons here, but you kind of know what this picture would look like if I just kept going. The idea here is, if I added up all of these individual photon polarizations, the net would be 0. So there is no net polarization direction to this collection. Now that it's important, this is not a sloppy state of polarization. This is actually a very special state. This is perfectly random. Okay? I like to contrast that with a situation which maybe looks like this, where I have a bunch of photon polarizations. They're not perfectly aligned, but if I add them all up, I get something which has some net direction. Okay, this is not linearly polarized, neither is it unpolarized. Okay. So unpolarized light is a particularly special configuration of polarizations. It's a perfectly random collection of photon polarizations. The last special state of polarization that we're going to consider is circular polarization. Okay. And we're going to talk about that a little bit later. All right, well, we're going to focus for the first part of the morning on linear polarization, to some degree unpolarized light, but mainly linear polarization. We're going to talk about things we can do with it. We're going to break for a short activity, and then after that short activity, we'll come back and talk about circular polarization. The discussion of circular polarization is slightly more mathematically involved. It's more abstract. People have a hard time visualizing circular polarization. So we kind of defer that after you've gotten a little bit of familiarity with the workings of linear polarization. So we'll talk about circular polarization in more detail after the activity this morning. So we have these three special states of polarization, and now we can ask, okay, if I create light, what kind of polarization state is it in? If I am given light in a certain polarization state, do I have a way of manipulating that? Can I change it? So the first question we can ask is, if I just have a generic source of light, like an incandescent bulb, what kind of polarization what kind of polarization state do you think the light is coming out of an incandescent bulb in? If you had to guess.
Unpolarized.
Yeah, if you think about it, this is a pretty random macroscopic system. It's got a collection of atoms. You're heating them up. They're wiggling in all these different directions. It's not a crystalline structure. Crystalline structures have a certain order, symmetry, so there you might expect some polarization. But this is a relatively soft structure. You heat it up, it's going to put out radiation in all directions. All the photons coming out are going to be randomly aligned. You've got a bunch of them. So generically, the radiation coming out of this is going to be unpolarized. Okay? So even though unpolarized light is classically a little hard to picture, in general, when we create light, it tends to be in a state of unpolarized, or in an unpolarized state. Okay? So one thing we might like to do is to take that unpolarized light and render it polarized. Now, there is at least one situation I can think of where we can create polarized light. Anybody have an idea?
Sodium glasses.
That's getting a little further ahead in the story, and we'll talk about that. This is creating light, not manipulating light, but creating light that's polarized.
LCD screens.
So is laser light polarized?
Yes.
Who thinks laser light's polarized? Grandpa waiting. Who thinks it's unpolarized? Well, the tricky thing is that the laser light coming out of your lasers is polarized, but laser light itself is not polarized. The light coming out of your lasers is polarized for a different reason that we're going to talk about. Okay? But generically, laser light does not need to be polarized. At some level, that might depend on the properties of your lasing medium. But if you think about it, these are Heaney tubes. It's gas. The photons are being created through interactions with gas, and gas has a lot of randomness to it. So the photons being created, there's no reason why their polarization axes should line up. So what form of light emission can you think of that would be polarized in a particular fashion? I'll give you a hint. I talked about it about 19 minutes ago.
Is that wiggling the charcoal on a wire?
Yeah, a linear dipole antenna. You control the direction in which the electric field is oscillating. When that radiation leaves the antenna, it has to have the electric field oscillating in the direction of the axis of the antenna. So you can control that. That's why I said that linear dipole antenna is nice, because you have a lot of control over the feature of the electromagnetic radiation that it's putting out. So we can create linearly polarized light. We can create unpolarized light, but how can we manipulate them? Okay, so let's now talk about topic of polarizers. And polarizers come in two forms. We'll start by talking about what are called absorptive polarizers, or sometimes absorptive filters. Or no, we'll say absorptive polarizers, I don't want to say filters. And the means by which an absorptive polarizer works can vary from one device to another. But the effect of a linear polarizing filter and absorptive polarizer is the same. So I'm going to illustrate the effect of it as sort of a black box. So what happens with an absorptive polarizer is, if I have some light coming in that's maybe polarized in the vertical direction, actually let me put it at a more arbitrary field, say that way, then the linear polarizer is just some device that has associated with it a preferred axis, and we call this the polarization axis. Of the filter. And what a generic absorptive polarizer or polarizing filter does, it takes the polarization coming in and it decomposes it into a component which is parallel to the absorptive, or to the polarization axis, and a component which is perpendicular to the absorptive axis, to the polarization axis, sorry, and it blocks or absorbs the component perpendicular to the polarization axis of the filter. So what emerges is light which is now polarized parallel to the polarization axis of the filter. So, to some degree, we could say that a polarization filter, or an absorptive polarizer, rotates the polarization of the light. But does it really rotate it? Right, when we think about rotation, we tend to think of rotating something, but it doesn't change its size. Will the size of this be the same as the size of what went in? No, in fact, you could probably tell me how big this is compared to what went in. If this comes in at an angle theta to the polarization axis of the filter with an intensity I naught, what is the intensity I out, or I'll call this I in? What is the intensity coming out? So yeah, you decompose this vector, and so you'd say I n times cosine theta. Okay? It's actually cosine squared theta. Why would it be cosine squared theta? Because I said so? It's a good reason. Now, why might it be cosine squared? I mean, I know why you said cosine theta. What'd you do? You decomposed the electric field?
There's also a magnetic field.
That's a really good guess. But when we're talking, so the intensity of an electromagnetic wave you can actually express entirely in terms of the electric field itself. Because once you know the electric field and its behavior, you can use Maxwell's equations to infer from that the behavior of the magnetic field. So they're not independent quantities.
So you get rid of the negative?
It does get rid of a possible negative. I totally agree with you on that. Squaring it will do that for us, but I don't think we get to arbitrarily square things just because we don't like negative signs. Sometimes we do in different courses. Yes?
Isn't the intensity proportional to the square of the electric field?
Exactly. The intensity of a wave is proportional to the square of the electric field. The electric field is the vector, and that's the thing you decompose and get the cosine theta, but then the intensity depends on the square of that, so you get a cosine squared theta. This result is called Malus' law, and it tells us how much intensity we can expect for light coming out of a polarizing filter based on the angle that the initial polarized light makes with the polarization axis of the filter. So this leads us to an interesting possibility. If I have a polarizing filter and I send in light which is polarized at exactly 45 degrees to the axis of the filter, how much light comes out? Half, okay? Cosine of 45 is 1 over root 2e squared, then you get 1/2. I don't know about you, but that just feels good. You know, it's halfway between a long and perpendicular, about half should get through. It's, you know, it's the one thing I don't like about trigonometry. Cosine and sine of 45 isn't a half. Damn it, it feels like it should be a half. But the good thing is that physics makes it a half. Physics cares about the square. But anyway, so it's a half, all right? But here's another interesting possibility. What if I sent in unpolarized light? What intensity would I expect to get out?
Half.
I would actually get out half. You're exactly right. Now, understanding why you get out half is actually a somewhat advanced story. We don't have a classical picture of the electric field vector we can draw. Rather, we have all of these photon polarizations. And the question is, how does the polarizer affect these photon polarizations? Okay. Well, you might think that the polarizing filter takes each of these polarization vectors and decomposes it into 2 pieces, but that's kind of like breaking a photon in half, which you can't do. So when you eventually take Physics 320, quantum mechanics, and you might have seen this idea in your modern physics class depending on who taught it to you, what you'll actually learn is that in the quantum mechanical version of this, the angle that the photon polarizations make with respect to the axis of the polarizing filter actually corresponds, the square of that, the cosine of that corresponds to the probability of that photon making it through. So, for example, if the photon's polarization is parallel to the axis, the probability of it getting through is 1. If it's perpendicular, it's 0. If it's 45, it's got a probability of 1/2 getting through. Moreover, once these photons pass through the filter, their polarization axis, the ones that do make it through, is then aligned with the polarization axis of the filter. This is all a story that should be borne out in great detail when you take Physics 320. This is a scenario that's often called a Stern-Gerlach experiment, which is originally done with spin-and-a-half particles, but they obey the same sort of, or they exhibit the same type of behavior. Nonetheless, is everyone on board, at least? Does it feel okay that if I send in unpolarized, I get half of the original intensity out? Under the quantum mechanics underpinning that, you'll get to learn later. Now is an interesting question. And I like to ask this question because this points to issues that we're going to encounter throughout today's activities, and that is the ambiguity of polarization experiments. Many times when you do a polarization experiment, you get some information out, but you don't get all the information. And sometimes you have to do a lot of work, maybe you have to do subsequent experiments to get more information out. So consider the following. If I gave you a light source and a polarizing filter, and you sent the light source through the polarizing filter, and you got half the intensity out the other side, what could you say about the incident light source? Yeah, you could say it's one of these two, but you don't know which one. All right? You definitely know it's not linearly polarized at, some weird angle, but it could be at 45 or it could be perfectly unpolarized. So with that one experiment, you can conclude that it's one of these two, but nothing more. Now, how could you figure out which one of these two it actually is?
I don't know. I was kind of going to ask, for unpolarized light, does it matter what the axis is? Will you always get half the intensity?
So you're moving on to the right answer to this question, which is, what could you do?
So you could just have like a tilted, or one with like a tilted polarization axis, and if you're still getting half the intensity, then it's not 45 degrees.
Exactly. If you rotate your polarizer, this result won't change. But if you rotate the polarizer, this result must change because you're rotating it with respect to this linear polarization direction. Okay? So that you're exactly right. That's exactly the answer to the question. For unpolarized light, it doesn't matter because there's no preferred direction. But the point I'm trying to get you to see is you have to do 2 different experiments in order to discern which of these 2 possibilities you're looking at. So keep that in mind today because when we work with polarization, a lot of times we make one measurement and we don't have the complete answer, we have to do other things to fill out the information of what's really going on. Yes?
How would you tell the difference between like 45 and 135? Or like 1/3 cosine squared is the same.
45 and...
Where cosine squared is 1/2, because there's more possibilities.
Oh, yeah. No, that's actually, yeah, no, you're exactly right. You are totally right, okay? So there are three possibilities that you could infer. So you could also have this scenario, where this is a 45-degree angle. That's what you were calling. So when we talk about the interaction of polarized light with a polarizing filter, the only thing we care about is the angle that the polarization direction makes with respect to the axis of the filter. Now remember, these are bidirectional arrows.
Yeah.
So first of all, it doesn't matter if I go this way or this way. It's still 45 from the axis. You could call one of them positive 45 and one of them negative 45, but the cosine doesn't care. Moreover, if you try and take it even further and take it to 180, past that doesn't care because it's a bidirectional arrow. But nonetheless, these are two possibilities. I would call them both polarized 45 degrees from the axis, but they're different from each other, okay? However, if I rotate this polarizer, I would definitely know which of these two I was experiencing. Because eventually I would be, for example, aligned with this one. So all of it would get through, but not aligned with this one. So you could resolve which of these two you were in if you were in one of them by rotating the filter as well. Okay, so those are polarizing filters. There's another type of polarizer that we encounter, and it is called a beam splitting polarizer. And the way a beam splitting polarizer works is instead of taking the light and just filtering off part of it, thereby changing state of polarization, it takes a beam of light or a source of light and it splits it into two different directions, two different beams. And in a beam splitting polarizer, we usually have information about the polarization of at least one of those beams. Maybe not both of them, maybe both of them, depending. But at least one of those beams, we have some definite information about the polarization. So let's look at an example of one beam splitting polarizer and how that might actually work. So we actually learned in our first day together how to split a beam of light. So the simplest way is to have that light incident on a surface, and the incident beam, when it hits a discrete interface, gives rise to a reflected beam and a refracted beam. So my original source of light is now split into two beams. And we can try and infer some information about the polarization of the beams that result from this. Now generically, to get information about the polarization is quite tough. But there's one special scenario where we get a really nice result. I'm going to wave my hands to kind of give you an intuitive explanation, but the truth is it merits deriving it in more detail, which maybe you'll get to do in your advanced electromagnetism class, I don't know. But consider the situation where the reflected beam and the transmitted beam, the reflected and the refracted beams, are at 90 degrees to each other. Okay? That is not generically the case. Now you can find, if you know the index of refraction of the incident medium and the index of refraction in the refracted medium, you can find what angle of incidence would give you this condition. That's just a math problem. Okay. What you're looking for is the condition where the reflected angle and the refracted angle add up to what?
90.
Yeah, 90. Because each of these are their complements, and they have to add to 90, and the whole thing has to add to 180. Don't get confused. That's clearly not 2 theta r. You guys know better than that. This is theta reflected. This is theta refracted. Okay, so you get the refracted angle in terms of the indices of refraction. So there's a little math problem here, but if I gave you two materials, I gave you their indices of refraction, I could ask you, calculate the angle of incidence that gives me this scenario. And you could do that. Okay. Now this scenario is special for the following reason. Let's talk about the polarization of the light coming in to this, coming onto this discrete interface. So the polarization of the light coming in has to be perpendicular to the propagation vector. So that's the propagation vector is the blue line. So I have this plane which is perpendicular to the blue line. So my hand is kind of the plane in which the polarization can point. And I'm going to pick for my directions in this plane two special convenient directions. One is coming straight out of the board. And the other one then has to be in the board along the plane of my hand, so it'll be something like this. And notice both of those are transverse to the propagation vector of the wave. Now these have special names. This guy is called P polarization, and this guy is called S polarization. The origin of these names is in German, which if you speak German, good for you. We'll go find the words. And this might be intuitive, this labeling scheme. The way that we tend to remember it is that the S polarization skims the surface, but the P polarization pierces or plunges into the surface. This thing kind of stabs the surface. So that's just one way of remembering it. But we do want to keep these straight, which is S and which is P. We're going to talk a lot about S and P throughout today and in the activities. Okay. So why are we picking on S and P? Well, let's consider for a moment that light comes in and it is polarized only in the P direction. So it's linearly polarized and it's wiggling this way. Now, I'll work up my fingers because I'm about to wave the crap out of my hands. This is a non-rigorous, hand-wavy argument for a result that is in fact true and can be derived in a more rigorous fashion. When this light hits the surface, let's kind of try to argue how these refracted and reflected beams come about. So the simplest description of that, the lowest approximation for what's happening, is that the electric field from the incident wave hits atoms or molecules on the surface and induces the electric charges there to wiggle. And they have to wiggle in the direction of the incident electric field. Now, those wiggling electric charges are going to act like a linear dipole, and they will generate waves. The idea, though, is that the maximum in that linear dipole pattern is in the direction of the refracted wave. Okay? And there's a lot of smoke and mirrors around that. But generally speaking, to understand this phenomenon, we just have to accept that the maximum of the induced linear dipole transmitter, caused by the incident wave wiggling the electrons, for example, is along the refracted direction. However, for this particular situation, what is the intensity of the reflected wave?
0.
Why?
E and K are parallel.
Yeah, so remember our linear dipole pattern? If our dipole antenna is along the axis here, perpendicular to the refracted direction, then there's 0 intensity emitted along the axis of the antenna. So we have the intensity of reflected light is 0 if the incident light is P-polarized at the angle that gives us 90 degrees between the reflected and the refracted beams. There's a lot of things that have to happen in order for this to be true. This does in fact happen. And the angle of incidence that causes this gets a special name from the guy that analyzed and first understood this effect. It's the Brewster angle, and this is the Brewster effect. Okay. So here we'll get refracted light, which has some non-zero intensity. In fact, for this particular situation, it's the full intensity of the incident beam. But now let's go back and talk about more general states of polarization. So what would happen if I sent in light which was S-polarized onto this surface? Well, S-polarized light would hit the surface. It would cause electrons to wiggle perpendicular to the board. But a dipole antenna perpendicular to the board can emit radiation in this direction or in this direction because they're both perpendicular to the antenna. So if I send an S-polarized light, I generally get reflected light with a non-zero intensity and refracted light with a non-zero intensity. But this now allows me to do something interesting, because what I can do now is send in light that has both S and P polarization. Okay, so I can send in a mixture of S and P polarization. As long as that light is incident at Brewster's angle, the P part of it cannot reflect. Only the S part can. So our light reflected off the surface, if it's incident at Brewster's angle, will only have S polarization. The refracted light can have both. Okay. Now you might say, well, how do we get light with mixes of S and P polarization? Well, unpolarized light would be a 50-50 mixture of S and P polarization. Anything that's not perfectly S or perfectly P is a mixture of S and P. And what this surface will do is it will strip off the S component and only allow that to reflect. Okay? Now everybody look at your laser tubes. You notice how they're slanted? The window where the laser comes out? See how they look like somebody cut them diagonally? You ever wonder why there's a funny angle there? That is called a Brewster window. And that Brewster window is using the Brewster effect to create polarized output from your lasers. So this is why your laser output is polarized. It's not that laser light itself is intrinsically polarized necessarily, but the tube is designed with this window utilizing the Brewster effect to get the output to be linearly polarized. So this is an example of a beam splitting polarizer. Again, we can send in arbitrary state. One of the beams coming out has a known polarization. The other one we don't know too much about, but that's okay. But we can make use of this, and you know, quite a few people in the room probably know the story I'm about to tell, but I'll tell it anyway because it's fun. After field session, Steve and I go to Hawaii, and Steve drinks Mai Tais. Mai Tais are the drink of Hawaii. I've discovered it. Confused about that for a while. And he likes to go to those nice cliffs of Hawaii and drink his Mai Tais and stare out over the vast, beautiful ocean and contemplate jumping in for a refreshing dip in the cool waters on this hot summer day in Hawaii. But what Steve is not aware of is that waiting for him in that water is Jaws, which I always thought was a funny name because the shark has one jaw. Why did they call it Jaw? But anyway, you know, just to keep the spirit of field session, Jaws is a very bad shark. You know, bad sharks have red eyes and red teeth and lasers. But anyway, Steve's going to jump in the water and meet Jaws. The problem is, it's not that Steve is dumb. It's that when Steve looks at the water, he doesn't see Jaws. Because the problem is the sun, the sun's shining down. It's Hawaii. The sun's shining. It's not Colorado or Seattle or places like that. The sun is shining down. Some of the sunlight goes in the water, and it can bounce off Jaws and go up and into Steve's eye, and that would give Steve a way of seeing Jaws. Okay. But the problem is a lot of the light is actually reflecting off the surface of the water. And that is a very strong reflection. So Jaws is basically hiding under the glare from the light reflecting off the surface of the water. However, I, having died from choking on the banana, am now an angel in Hawaii. And I still like Steve, even though I'm dead. And I decide to save Steve's life before he jumps in the water by handing him a very special gift. And what is it that I give him?
Sunglasses.
So not just any sunglasses.
Polarized.
Polarized sunglasses. Why are my polarized sunglasses going to help Steve? Well, if we think about the light as it's bouncing off of the surface of the water, some, not all, but some of that light is going to be incident at Brewster's angle. Now this sunlight is largely unpolarized, so when it comes down it's a mix of S and P polarization, but the light that's incident at Brewster's angle is going to reflect, and when it reflects and goes towards Steve's eye, it's going to be in what state of polarization?
S.
S, the only state it can be in. So that light is going to be S polarized. Okay? I can take a pair of polarized glasses and put them on Steve, and if the axis of polarization, remember S polarized is like this, oh sorry, that's P. S polarized is out of the board. If the polarization axis of the polarizing glasses I give Steve is in the P direction, then those polarized glasses will absorb or block the S polarized light reflected off the surface. They will reduce the glare off the surface of the water. So that's one part of the story. It reduces the light reflected off the surface of the water through this filtering of polarized light induced by the Brewster effect. However, we also have light that comes in, transmits into the water, bounces off the shark, and comes out of the water, goes to Steve's eye. However, when light is refracted, we do not get a Brewster effect. Moreover, when we move from a high index of refraction to a low index of refraction, okay, we're not going to get the Brewster effect in the same configuration. So generally speaking, we're going to filter light reflecting off of the surface, but we're not going to filter the light reflected off of the shark. And so when he puts on the glasses and looks in the water, lo and behold, he'll be able to see the shark through the glare reflected off the surface of the water. How many of you have put on polarized glasses and looked at a creek, for example? You should all do that. It's worthwhile. They have to be linearly polarized. Don't grab the circular polarized glasses from your local 3D movie theater. Okay, so that completes our discussion of linear polarization for now. And what we're going to do is break and work on an activity concerning linear polarization, and then I'll come back and talk about circular polarization a little later. So go ahead and start reading through the directions for the microwave activity, and while you do that, I'm going to give you some equipment. So you're going to want to find a space in about 2 feet or so to set things up. Nothing's getting bolted down, so don't.
Yeah, we did it. Oh, it's fast.
Sounds good.
First of all, body's attention. What you have here are microwave emitters and receivers, and these are devices which you probably used at some level in Physics 200. One of them has a meter on it. That's the receiver. The other one is the transmitter. The transmitter you just plug into the power source that we've provided to you. And when you plug it in, there's no on or off switch. It just, the red light will come on and it should be generating microwaves. Now, the nice thing about microwaves is that they have really long wavelengths. Anybody know the order of magnitude of the wavelength of a microwave?
1 E minus 6.
Say it again?
What's a microwave? So a microscale, so 10 to the minus 6. Wavelength.
That's a good guess. I like the guess. Any other guesses?
About a meter?
Meters? Do you know the exact wavelength of these by any chance?
I do.
What is it?
They should too.
You guys should too, apparently.
3 centimeters?
3 centimeters? So think about that in comparison to visible light. What are the wavelengths of visible light?
Nanometers.
Nanometers. Tiny. Okay? These are, you can actually do this with your fingers. Everybody show me 3 centimeters with your fingers. Now, if the wavelength is 3 centimeters, what can you tell me about the frequency? Is it small or large?
Small.
It's small, it's very slow. Remember, the speed of light is the wavelength times the frequency. If the wavelength is very large for these, then their frequency is very slow. So if you think about it, this is a big-ass wave wiggling really slowly. Which is nice because it means that we can manipulate this wave classically. We can actually just rely on classical ideas from electricity and magnetism to manipulate this. For visible light, it's moving so fast, its wavelength is so small, you really have to take quantum mechanical effects into account to manipulate that. Okay, we will manipulate the polarization of visible light later today, but for now we're going to start with something which is so big and so slow that we can actually just work with it classically. So this guy is transmitting a microwave. Cool. All right, this is not tuned to the resonant frequency of water, so you do not have to worry about shining it into your face. So what's actually going on inside of here is pretty straightforward. There's a wire, and there is an alternating current moving through that wire. An alternating current moving through a wire is basically a linear dipole antenna. This is transmitting. It's plugged into a power source. Power goes in, electromagnetic radiation comes out of that linear dipole antenna. And it's linearly polarized. What you do not know is the direction of the polarization of that wave. Now, you look at this and you might say, oh, it's along the long axis of the horn, or it's perpendicular to it, or maybe it's at some weird angle. Maybe the person that made this was a madman and he put it at some arbitrary angle. I don't know! And you don't know either. Okay, that wire is hidden inside this box. You can't see it. You can't look at it and go, oh, there's the wire. Okay? The story of this is actually a little bit more complicated than that, because if you look at it, you'll actually realize that it's converting this to a direct current input. So you might wonder, how the hell do you get a linear dipole antenna out of a direct current input? If you want to know more about that, you can come and talk to me later. But the main concern here is that this is putting out linearly polarized light with 3 centimeter wavelengths, but you do not know the direction of the polarization of that. This device is a microwave receiver. It is essentially the same as this, but without a power source. There is inside of this thing a wire. And when the microwave from the transmitter hits that wire, the oscillating electric field will cause an oscillating current to flow in that wire. Now, the oscillating current in the wire in here is going to be very, very tiny. So small, in fact, that you can't really use mechanical means to detect it. So what we do is we put a battery in here so that when you turn this on, that red light should come on, and that battery is acting to beef up the response so that you can actually deflect the needle and see a reading. Okay? So you won't read anything until you turn this thing on. But once you turn it on, you can adjust the sensitivity depending on the intensity coming in from your transmitter. Again, inside of here is a wire, and you don't know the direction that wire is oriented. So your first activity is going to be taking these two devices and pointing them at each other and rotating them and trying to determine when you've achieved a relative alignment of their polarization axes. You don't know absolutely anything, but you can at least say they are aligned relative to each other. The way we're going to get more information out of this is by using this incredibly sophisticated device, which is called a piece of metal with slits cut in it. Okay? That's genuinely all this is. You can forget about all this other machinery. That's something that you'll use in AdLab to study a more complicated scenario. All you really care about from this device is this round thing. And you can just think of this as a glorified stand for it. And this round thing is a piece of metal with slits cut in it. This will act as an absorptive polarizer for microwaves. Okay? I'm telling you that. That means that it has a polarization axis, and if you send in microwaves polarized at some angle to that, you will filter out part of the incident wave. Your job is to figure out, theoretically, what the polarization axis of this filter is. Okay, by thinking about what does light do when it hits metal. Once you've determined the polarization axis of this filter, then you can start doing experiments with the transmitter and receiver and the filter and figure out what the actual polarization directions in these devices are. Okay? So again, what I'm trying to illustrate to you is this ambiguity. Before you use this, you can figure something out. You can figure out when these are aligned or when they're perpendicular, but you cannot figure out the absolute direction of either one of them. But by understanding this polarization filter and then adding that to the experiment, you'll be able to determine more information. Okay? So with that in mind, I'll let you guys start on these activities, and we'll work on these for 20 or so minutes, and then we'll finish up this morning's lecture. I'm going to cut you off there because we've got some groups that are done. We've got some groups that are just writing up the last bit, and you'll have time when we finish with this part of the lecture to complete your write-up. But I'm going to go ahead and finish with morning's material, and then I'll let you all proceed with finishing up and or is everyone actually done with the equipment? Everybody's done with the equipment. Greco, will you collect the equipment? Especially the power sources. Okay, so get comfortable. We're going to talk for 20 or so minutes, and then I'll turn you on to the rest of the activities. First of all, when you go to the activities this afternoon, you're going to be dealing with visible light. And the main reason why I had you work with the polarizer, the microwave polarizers first, is because once you get to the visible light, the wavelengths are so small, the frequencies are so high, that you actually start, having to deal with working with quantum mechanics to explain exactly what's going on. And the downside of that is you can't see. You can't see quantum mechanical size things. So if you look through a visible light polarizer, okay, you don't see slits, you don't see these combs, and you can't just sort of figure out the direction of the polarization axis of the filter. In fact, when you look through an optical polarizer, it just looks a little dim. All right. You've got 3 of these today, and so when you work with today's activities, you're going to take these and you're going to work with a few setups to determine the polarization axis of each of these. They're mounted in these brackets with angular demarcations, but you do not know what angle corresponds to the polarization axis of these filters, and in fact, we set them to be random. But your job today, one of your jobs today, is to figure out those directions. But you can immediately take these and play with them. You can put them on top of each other and rotate them, and you know that when you cross them, you'll get nothing coming through. Okay. However, again, that just tells you that they're relatively crossed. It doesn't tell you the absolute polarization axis of either one of them. So today's activities are going to become even more subtle than what you did with the microwaves because you don't have this, sort of visible picture of the slits that you can infer information. But before we get to working with today's activities, I need to talk about this last form of polarization. And in order to talk about that, I'm going to start with a more broadly applicable description of polarization. So it's going to be a little bit of math here, but we'll try and make it manageable. So here I've got the plane of polarization. So the propagation vector of the wave is coming out of the board. So the polarization has to be somewhere in this square, in this plane that I've drawn. And I've just set up an x and a y axis just for convenience. That's one way to talk about directions in a plane. And so now what I want to do is I want to write down expressions for the x component and y component of the electric field for this wave as it's propagating along the z-axis, which, in this situation points out of the board. So the expressions I'm going to use are Ex cosine kz plus omega t and Ey cosine kz plus omega t plus phi, where phi is just an angle that I can use to adjust the relative phase of the x and y components. And that's going to be an important parameter we can play around with. But otherwise, the form of these should be somewhat familiar to you from Physics 1 and maybe from Physics 2. These are just the amplitudes along the x and y directions, and then you have a cosine of kz minus omega t or kz plus omega t. It's the usual argument of the trigonometric function that corresponds to a wave traveling along the z-axis. So k is the wave number, with a magnitude of 2 pi over lambda and omega is a circular frequency. So what I want to do is take these expressions and I want to assign different values for things and try and extract from that what kind of state of polarization I'm describing. So to start with, let's start with one that might be a somewhat intuitive result. Let's start with Ex being equal to Ey and the relative phase angle being 0. Okay? Now what I want to do is I want to plot as a function of time what is happening to the x and y components of the polarization. Now, when we talk about looking at the polarization direction for a wave, waves are, they're moving in 3 dimensions and they're oscillating in time. So the one way to kind of cut this down to a manageable picture to analyze is to just pick a point in space, a plane that's cutting the wave, and then imagine what the wave looks like as it passes through that plane. So we might as well just pick the z equals 0 plane and just ask, what's the electric field doing as the wave moves through that z equals 0 plane? Okay, so for all intents and purposes, we could just set z equals 0, and then as time increases, we're basically looking at the angle in here increasing with time. So I'm going to call this angle delta. And delta is just going to basically play a proxy for time. As time increases, delta increases. The difference being the time increases, in seconds and goes 0, up, 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 up. But delta goes 0 to 2 pi to 2 pi to 2 pi to 2 pi. Okay. So let's start by asking at delta equals 0. That's kind of like our t equals 0 point. What is the x component of this wave?
Yeah.
Yeah, at delta equals 0, cosine of 0 is 1, so the x component is just Ex. So we get some Ex component to our wave. What is the y component of our wave?
Ex.
It's the same, because if phi is 0, then this is just cosine of delta, which means cosine of 0, which is 1, and then I set Ex equal to Ey, so it's the same. So I have these two pieces that are pointing in the same direction. Or sorry, I always do that. I did that last time. I get a component in the y direction that's the same size as the component in the x direction. Okay. If I add those together, what does the total electric field look like at delta equals 0? Yeah, it's just something pointing off at 45 degrees. I'm going to go through this the first time very slowly, and then in subsequent examples we'll go through very quickly. Now let's go to delta equals pi over 2. Let's let time advance until delta equals pi over 2. What's the x component of the electric field at delta equals pi over 2? The y component?
0.
Good. So at delta equals pi over 2, if I add together 0 and 0, I get 0. So my electric field is 0. What about when delta goes to pi?
Negative.
I get negative Ex for the x component and the same size component in the negative y direction. If I add those together, I get something pointing like so. That's my delta equals pi contribution. And then if I advance to delta equals pi over 3 pi over 2, everything goes back to 0. And lo and behold, what state of polarization does this particular assignment describe?
Nearly at pi over 4.
It's linearly polarized at pi over 4 to either the x or y axis. It doesn't matter. Okay. So these expressions are powerful enough to describe a state of linear polarization at least at 45 degrees to the axis. Well, let's see what else we can get out of it. What if we took Ex to be larger than Ey and the relative phase to be 0? What then would happen? Well, we can now do this much quicker. At delta equals 0, we get an x component to our vector, and we get a y component, but the x component is larger, so when I add them together, I'm going to get a delta equals 0 contribution, which is tilted towards the x-axis. At pi over 2, both are 0. At pi, I get the same relative x and y components that I got at delta equals 0, but with the signs reversed. So when I add those together, I'm going to get the vector like so. And then at 3 pi over 2, I get 0 again. And so what state of polarization am I now describing? Right, it's still linear polarized light, but the angle of polarization is different. And hopefully now it should be clear that I can use these expressions to describe any state of linear polarization at any angle. Right, I could take Ex to be something and Ey to be 0, and that would be just polarized along the x-axis, and I can pick any other angle I want. Okay. So we can describe any state of linear polarization as long as we choose the relative phases to be 0. But now, of course, we want to explore what happens when I set the relative phase to be non-zero. So let's consider, to start with, let's go back to equal amplitudes. This will be a little bit easier. And now what I want to do is take the relative phase to be pi over 2. That'll be a number that's pretty easy to work with. So let's think carefully now. At delta equals 0, what is the x component of my electric field? It's Ex. What is the y component?
0.
0. Okay? Because at delta equals 0, this is 0, but I still have the pi over 2. Cosine pi over 2 is 0. So at delta equals 0, I have an x component to my electric field only. What about when delta is pi over 2? So what is my x component?
0.
My x component is 0. My y component is negative Ex. Okay, because at pi over 2, I get pi over 2 plus pi over 2, which is pi. Cosine of that is minus 1. So now I get a negative component in the y direction that has the same size as what I started with. Okay. If I proceed to pi, then my Ex component goes back to minus Ex, and my y component, well, this is now cosine of 3 pi over 2, which is 0, so I only have a negative, or I only have an x component that's along the negative axis, and so there's my pi electric field. And lastly, if I go to delta equals 3 pi over 2, as you could probably guess, I get an electric field along the y-axis, and so what are we now describing?
Circular polarization.
Yeah, we're actually describing light where the direction of polarization is spinning in a circle. This, of course, is circular polarization. Now that might bother you. I mean, you might think, well, wait a minute. You know, when light moves, the electric field is oscillating. This is somehow saying that it's not oscillating; it's spinning. But you might recall that in Physics 1, you learned that if you have uniform circular motion, you can consider uniform circular motion as a combination of harmonic motion in the x and y direction. And that's all we're doing here. We're taking simple harmonic oscillation in x and y and combining it in just the right way so that the net effect is basically uniform circular motion. Okay. So this is circular polarization. We can switch the sign of our relative phase and we can get a counterclockwise. So this is clockwise or right-handed. Is that right, Greco? Yep. Yeah, right-handed. We can switch the sign of the relative phase, and in that case, you can work this out, and you'll find that it rotates counterclockwise. Right? We call that left-handed polarization. And so we have these two distinct states of circular polarization, clockwise and counterclockwise, and they, again, remember I said we could, when we describe polarization, we could work with an x and y basis, or we could work with a counterclockwise or clockwise and a counterclockwise basis. Okay. Each of these bases are a perfectly suitable way to describe a state of polarization for an electromagnetic wave. Okay, we'll talk about interchanging between them in just a moment. We can do something a little bit more general. What would happen if I, for example, chose EX greater than EY and kept the relative phase at pi over 2? What would that describe? Yeah, that would describe a state of elliptical polarization where we actually sweep out an oval. What if I took the limit where EX was non-zero and EY was 0? What would I describe?
Linear.
I would go back to linear. Because if I set EY to 0, the relative phase doesn't matter because there is no oscillation in the y direction. So the limit of this is actually linear polarization. Okay, you squash a circle flat enough and it becomes a line. Okay. Now, I want you to notice something. We've got this new state of polarization, circular polarization, but our description of it was actually in terms of x and y. Okay? So we can take a state of circular polarization and we can think of it in terms of a combination of linear polarizations. And you might ask, well, can you go backwards? Can you do it the other way? Can you think of a state of linear polarization in terms of a combination of states of circular polarization? And to see that, we just take two waves, maybe one that is right circularly polarized and one that is left circularly polarized. And we just imagine adding up their electric field at each instant of time. At delta equals 0, they're both pointing to the right. At delta equals pi over 2, this one's pointing down along the negative y, this is pointing up along the positive y, so they add to 0. At pi, they're both pointing along the negative y. And at 3 pi over 2, they're both canceling again. And lo and behold, a state of clockwise and a state of counterclockwise circular polarization adds together to give me a state of linear polarization. Okay? So we can describe circular polarization as a combination of linear polarization states, or we can describe linear polarization as a combination of circular polarization states. Mathematically, that's a nice thing. Okay? We can switch from one description to another. It actually turns out to be very important in devices, because there are devices which say, I only care about circular polarization states. And there are other devices that say, I only care about the linear polarization states. If you feed a device that only cares about linear polarization circularly polarized light, it's going to take that circularly polarized light and it's going to think of it in terms of linear polarization. And vice versa if you have a device that only cares about circular and you feed it linear. Okay? And we'll talk about those kinds of devices in just a minute. All right, so any questions right now about circular polarization? Yeah.
Why is clockwise called right-handed?
It's actually a convention, but the way that we tend to think of it is if you put your thumb in the direction of the propagation, and you're imagining this from behind actually, so that's maybe why it's backwards.
Okay.
And Chip said that the convention was. So normally we've got something twisting in a circle around a vector. Okay, so I can associate the twisting one way and the twisting the other way with handedness, right? Because if I have the thumb here and I curl my fingers, they twist around my thumb in one direction, and if I do the same with my left hand, they twist in the other direction. And then there's a matter of convention of what this vector is.
So you're watching it from behind then?
Yeah, so it turns out if this is right, you're watching it from behind. And I can't remember, I'm not an optician. I tend to think of the same thing in terms of chirality, the spin of atom, or the spin of elementary particles, where the same thing has to be used. And there we always think of it in terms of the velocity of the particle, and then the projection of its spin along its velocity axis. It's called the helicity. But anyway, opticians might have a different convention, but it doesn't matter. One of these is right-handed and one of them is left-handed, and that's the important thing. We're not too worried about which is which, okay? But as long as we understand that, clockwise is definitely distinct from counterclockwise. I mean, I can call this Adam and I can call that Steve. It doesn't matter, they're just names. Okay, so now let's talk about materials. Any other questions about circular polarization? Because now we're going to talk about stuff. All right, so stuff.
Now initially, I'm going to start talking about something which seems disconnected from circular polarization, but we will come back to circular polarization in due time. So the first thing I want to talk about is a property of materials called birefringence. And this turns out to be an incredibly useful property of materials, and the property that you can actually get from a material relatively easily. So birefringence is basically the following. If I have some hunk of material, okay, if that material is birefringent, then what that means is that in this material, there is some special axis called the optic axis of the material. Not the optical axis, that's the thing we used in ray tracings. This is called the optic axis of the birefringent material. Now when I say it's an axis, that's a little bit misleading because it's not a line in space, it's instead a direction. So everything in this direction is along the optic axis. Anything perpendicular to that is orthogonal to the optic axis. Now what's important about the optic axis in birefringent materials is the following. If I have a wave moving, let's see how I'm going to write this. If I have a wave moving through the material, then what we find is that if the polarization of the wave, that is the direction in which the electric field is oscillating, if the direction of the polarization is parallel to the optic axis, then the light moves through the material with some index of refraction. I'm going to call it N1. Okay? However, if the direction of polarization is perpendicular to the optic axis, then the light actually moves through the material at a different speed. That's not typically what we would expect. We would think if light moves through a material, it just moves through the material at a certain speed and it doesn't matter what direction the electric field is wiggling. But for birefringent materials, it's critical to know what direction the electric field is wiggling and how that's oriented with respect to the optic axis of the system, of the material, because that controls the speed of propagation. That sounds like a weird effect, but it's actually incredibly useful. So let's talk a little bit about it. First of all, how in God's name would you create something like this?
Crystal.
What about a crystal?
It's not the same in all directions, you're not certain.
Exactly, that's a great way to do it. So if I imagine a crystal, if it was a perfect cube, so if it's a cubic lattice, then you could imagine that if I just set up a little coordinate system, X, Y, and Z all look the same. So there's not one direction that's special compared to another one. But suppose that we had a material where the lattice was actually elongated along, say, one direction. So there's one direction, in this case the Z direction, which is definitely different than the X and Y directions. Okay. Now, why would that change the velocity of propagation of light? Well, when light moves through a material, the reason it slows down is because the photons are bumping into and interacting with the atoms or molecules in the material. Okay? So you can imagine that if it is easier to wiggle an electron this way, because it's further away from its nearest neighbors in this direction, then light might interact more strongly with it than if the light was trying to wiggle it this way. So if the light tries to wiggle this atom this way or this way, it's going to have basically the same level of interaction and move with the same speed. But if it's wiggling this way, then it's going to have a different amount of interaction with the atoms, and therefore it will move at a different speed. So what's the optic axis of this particular crystal? It's the z-axis. So light polarized along the z-axis would move through at one speed, and light polarized in some combination of x and y would move through at a different speed. Yes?
Does that mean if you move parallel to the optic axis, that's the like maximum speed you can move through that material?
So this is an interesting question. First of all, it depends on which of these two is bigger. I might suggest that this one is faster or slower than the other, but it depends. It depends. I don't think you always have to move faster if you're along the optic axis or not. I can't imagine that that's the case, because you could instead of stretching this, you could actually narrow it. So, but what the situation you're starting to talk about is actually an interesting that we should address. And unfortunately, this is probably one of the most complicated things about birefringence, is that it's a very three-dimensional thing. You can't afford to try and collapse it to 2 dimensions, because all 3 dimensions are very important. So for example, if a beam of light was moving through a material along the optic axis, how fast would it move? N1 or N2? It would move with the speed N1 or N2. So if this is the K vector,
N2. So the polarization has to be perpendicular to the optical axis.
right, the polarization has to be perpendicular to K, and if K is along the optic axis, then that means that it's polarized perpendicular to the optic axis, which means it has to move at N2. What if light is traveling perpendicular to the optic axis? What can you say? You don't know. Because if you're perpendicular, if your K vector is perpendicular to the optic axis, you could have your polarization along the optic axis, but you could also have it perpendicular. Okay? So when you think about birefringence, it gets really kind of weird. You have to take into account the 3-dimensionality of what's going on, the propagation direction, the polarization direction, and the optic axis. Okay? Now, you can do this with crystals, but it turns out that you can take a material and just give it some elongation, and that will induce birefringence. So if you want a cheap and dirty birefringent material, go home, go to your kitchen, get some saran wrap, stretch it, and that will exhibit birefringence. Okay. Now what can we do with this? Turns out we can do some really amazing things with birefringence. The setup that I'm going to show you looks a little bit tedious, okay, but we're going to use it a lot, so it's worthwhile to really try and take this in. Suppose that we take a piece of birefringent material and we create a little cavity out of it. Okay? And I'm just going to, for the sake of argument, say the optic axis of the birefringent material is horizontal. And what I want to do is send light in this end of the birefringent material, have it propagate through the cavity, and then come out the other end. Okay? And I want to talk about what this is going to do to the light. Now, suppose that I send in light which is polarized at 45 degrees to the optic axis. So what's going to happen is when this electric field hits the birefringent material, when this light hits the birefringent material, it's going to take this thing and it's going to break it up into a piece which is parallel to the optic axis and a piece which is perpendicular to the optic axis. And then they will move through the material at different speeds. Okay? We've already talked about that. But now I want you to think about the following. If this is a peak in the electric field, okay, so just think of it as a crest of a wave, then when it hits the birefringent material, that crest gets broken up into sort of a parallel and a perpendicular piece. And now as these move through the material, they're not going to move through together. One's going to move faster than the other. So when this guy hits the other end, he's not going to recombine with this guy. He's going to recombine with something from this axis which left earlier. Everybody on board with that? Now what we can do is we can choose the thickness of this piece of material And when we choose the thickness of this, we have to take into account the wavelength of light that we're using and the indices of refraction along and perpendicular to the optic axis. But if we know the wavelength and the indices of refraction, then we can choose the thickness such that when these two peaks combine at this end, one of them is 180 degrees out of phase with the other. So one way to envision that is if I took the peak here along the optic axis and I look at when that peak hits here, if I choose my thickness right, then the perpendicular component is 180 degrees out of phase when it hits here, so it's now pointing down. Okay. When I recombine these coming out, my new state of polarization is like that. Okay. Now, it's true, polarization we really should think of as a bidirected arrow, so this should really be something like this. So the state of polarization coming out is something like that. Yeah?
Are those 180 or 90 degrees off?
Well, that's so this angle is pi over 4, this angle is pi over 4. If all I've done is flip this over, then these are also pi over 4. Okay? So if I choose the thickness of this so that the phase shift is half a wavelength, 180 degrees, then I have constructed what is called a half wave plate. Now I want you to look at this and tell me, what does the half wave plate do?
Change the polarization of the wave.
Be more specific.
90 degrees.
Be more specific. How does it change it?
Rotates it.
It rotates it. Does it really rotate it?
No.
It combines a different part of it.
So compare this to what we talked about with absorptive filters. Remember we said an absorptive filter, you can send in one polarization and you get a different polarization out, but we argued that it did not rotate it because you changed the size. Is this rotating?
Yes.
It is. This gives us a means of actually rotating polarization without a loss of intensity. That is very useful. So half wave plates will rotate polarizations. Now let's talk about what rotation we get. I did the simple example of this being at 45 degrees, but you can see now that if the light came in at an angle theta with respect to the optic axis, the light coming out will basically be now at an angle theta below the optic axis, which means we've rotated the polarization by 2 theta. Now, this is important. If my light comes in polarized parallel to the optic axis, what does the half-wave plate do?
Doesn't rotate.
Doesn't.
Nothing, because theta is 0. If you rotate by 2 times 0, it's nothing. What if my light is polarized perpendicular to the optic axis? What does the half-wave plate do? Nothing, because the angle is 90. 2 times 90 is 180, but this is a bidirected arrow. If you flip it over, it doesn't change anything. So you only get something useful if the incident light is polarized at some non-zero or non-90 angle to the optic axis. Okay? And then the effect is a rotation around the optic axis by an angle, or a rotation, it's actually around the axis of the k vector by 2 theta, where theta is defined with respect to the optic axis. Okay? So half-wave plate, it's a nice little thing. And you're going to use these. And if you're wondering what one looks like, looks like that. Pretty much looks just like a polarizer. Okay, the only way you're going to know it's a half-wave plate is that it still gets 1/2 on it. So again, when we do visible polarization manipulation, everything is happening at such a small level that you can't actually see like what's going on. This is just going to look like a dirty piece of glass, right? But it's actually a birefringent material whose thickness is chosen specifically to create a half wavelength shift when you send 632.8 nanometer light through this. Remember, this depends on wavelength. So these things are designed to work with your helium neon lasers. If for whatever reason you're toying around the day and suddenly you need to use a green laser or alignment laser, these will not work properly. Okay. So there's one more case that we should consider that is it's basically the same setup, but what we're going to do is pick the thickness to be a little bit different. So suppose we sent in light polarized at 45 degrees to the optic axis. So again, we break this up into a perpendicular component and a parallel component. But this time, this is important, this time we're going to choose the thickness so that when the two pieces get to the other end, instead of being a 180 degree phase shift, there's a 90 degree phase shift. In this case, we have what we call a quarter wave plate. And now I will ask, if I send in linear polarized light at 45 degrees to the optic axis, what comes out of the other end of a quarter wave plate? Circularly polarized light. Because what is circularly polarized light? It's EX and EY of the same magnitude, but with a relative phase difference of 45 degrees. Or 90 degrees. Okay, that's why we did that analysis. This will only work, and now this is important, if you send the light in at 45 degrees from the optic axis. If you don't send it in at 45 degrees, you're going to end up with this elliptical pattern instead of circular. If you send it in along the optic axis, you're just going to get linear polarization out. This is not going to do anything. If you send it in perpendicular, it's not going to do anything. But at exactly 45 degrees to the optic axis, out comes circular polarization. So this is a nice device. It gives us a way of creating circularly polarized light. Again, it depends on the wavelength. Right? So the quarter wave plates you have, which are cleverly disguised with the sticker that says 1/4. Anyway, they're in there. They are designed to work for 632.8 helium neon laser light. Okay? Believe it or not, if you were given a half wave plate and a very fine knife, and you cut it in half, you would end up with 2 quarter wave plates. However, if I gave you 2 quarter wave plates, could you put them together to make a half wave plate? I would argue that you can take a half wave plate, cut it in half, and get 2 quarter wave plates. But can you take 2 quarter wave plates, put them end to end, and get a half wave plate?
Probably not.
You could, as long as you make sure that their optic axes are aligned. If I take 2 quarter wave plates and I don't align their optic axes and I stick them together, they are not going to act as a half wave plate. But if I make them parallel and then put them together, which is exactly what I would get if I took a half wave plate and cut it in half, then I'm guaranteed that they'll act as a half wave plate. So, quarter and half wave plates are going to be used extensively today. The important thing to remember about a half wave plate is that it allows you to rotate linear polarization without losing intensity. The importance of a quarter wave plate is that you can use it to create circularly polarized light. But you have to be careful and make sure that the incident light is polarized linearly at 45 degrees to the optic axis. Yes?
What happens if you put a circularly polarized wave into a half wave plate?
If you put a circularly polarized wave into a half wave plate, then it's going to break it up into an equal component along parallel and perpendicular to the optic axis with a relative phase shift of pi over 2, and then they're going to propagate to the other end, picking up an additional relative phase shift of pi, giving them a total relative phase shift of 3 pi over 2. So when they recombine, you're still going to get circularly polarized light out. Because
In the
having
same
a shift
direction?
of pi over 2 or 3 pi over 2 isn't going to make a difference.
Would it be possible to like change the direction of the rotation?
That's an interesting question, and I believe the answer is yes. I believe that that would convert right-handed to left-handed circularly polarized light, but I believe it would, but I'll have to think a little bit more carefully about it. Greco's over there with his eyes going, oh. I've never done it. I mean, you can certainly do it today, but I believe that it would convert right to left-handed circular polarization. I could be wrong. You think so? Have you done it?
Not personally. I think you can do it. You got to align things just right, but
Yeah. So, I mean, you're welcome to try that today if you want. One more thing very quickly that I want to talk about, and then we'll set you on to your activities today. So birefringence and these half-wave plates and these quarter-wave plates, you know, they're obviously useful because they can rotate linearly polarized light, they can create circularly polarized light. But the operation of birefringent material, the material itself, cares about linear polarization, right? When you move through the material, your speed of propagation depends on your state of linear polarization. You might ask, are there materials where the speed of propagation through the material depends on circular polarization? Oh, I totally forgot a part of the birefringent story, which I went straight to these complicated devices, and I could have said something simpler earlier. So for the sake of the video, I'll include this. With birefringent material, we can actually create a beam splitting polarizer. That's one more thing we can do. How do we do that? Well, if we have a birefringent material with some optic axis and we send a light beam in to the surface at some oblique angle, it's going to refract, but it's going to refract at different angles, depending on whether the polarization of the wave is perpendicular or parallel to the optic axis. So we can use birefringent materials and refraction to split the beam up. So this is a beam splitting polarizer. We can split the beam into two refracted beams of different polarization states, just because they're going to move with different speeds, and hence have different refraction angles. Okay. We won't do very much with this. We're going to work with wave plates, though, a lot. So, so again, all of the birefringence was focusing on the linear polarization of the light as it moved through it. We can instead consider materials that are called optically active. Materials. And in an optically active material, what happens is, as light moves through it, if the light is right circularly polarized, it moves with one speed, and if it's left circularly polarized, it moves with a different speed. Okay? So what does this mean? Well, one thing it means is if we send in a linearly polarized light, this material is going to look at this and say, I don't care about your linear polarization. I'm going to think of you as a combination of left and right, and then I'm going to let one of these move through at one speed and one move through at the other. So this is that comment I made earlier that you can use linear or circular polarization to describe any state of polarization you want, but there are materials that actually care about one over the other. Okay? What can you do with this? Well, you can do the same thing. You can create a beam splitting polarizer. But this time, when you refract at two different angles, and the resulting split beams are now left and right circularly polarized. Now, does anyone have any idea what kind of material would exhibit this property? So for birefringence, we said if the if the geometry of maybe a crystal has one direction in which things are elongated, then as light moves through, it's going to interact more or less strongly with the atoms, depending on whether it's trying to wiggle them along that direction or perpendicular to it. What is going to give us this?
The materials oriented in different circles, like directional circles.
So how do you have it? The
Um,
material is oriented in different directional circles.
Just a unique form of crystal or a different geometry of crystal, possibly.
So, unfortunately, fortunately or unfortunately, whichever way you want to view it, we can't really picture this so much in terms of looking at the geometry of the structure itself. And part of that is because for left and right circular polarization, there's no absolute axis that's important. With linear polarization, you can say, oh, it's linear polarized this way, and it's at this angle to this. So the geometry of your material can be compared to a state of linear polarization. But with circular polarization, it's not like, there's a direction I can point to and say that's the direction of circular polarization. Things are spinning. But if you think about it, what if you had a material that was made of things which themselves had a spin? So what I have in mind is, have any of you heard of chirality or chiral molecules? So you can have molecules which actually have a rotation in their structure. So DNA, it always rotates the same way. It's a handedness. You can take that molecule and you can flip it around and do anything you want, and you don't change the handedness. I can take my right hand and I can flip it any way I want, and it's still a right hand. It doesn't suddenly turn into a left hand. So if I have a material where I have more right-handed molecules than I have left-handed molecules, maybe I don't have any left-handed molecules, then you could imagine that when light moves through that material, if the light has a handedness that agrees with the handedness of the molecules, then the light might interact more or less strongly than the light that doesn't agree with the handedness of the molecules. So this optical activity we tend to observe in materials that have this chiral property, where they have either all of their geometries, molecular geometries, being right-handed, or most of them being right-handed and not left-handed, or vice versa. Okay. All right, any lingering questions? Okay, so what I want you to do is go ahead and finish very quickly writing up your microwave activities, and then read through the rest of the polarization activities before you get started. And the thing I want you to keep in mind is this notion of what you know and what you don't know. What's ambiguous after you make an observation? Because one of the things that we're going to have to work through today is figuring out the absolute polarization axis of these optical filters, which you can't get just by taking two of them and rotating them until they're crossed, because that only gives you relative information. To extract something absolute, we can't look at the filters. We don't see slits like this. Rather, what we're going to depend on is a phenomenon that we know tells us something about the absolute polarization direction, and that is the Brewster effect. Okay, so would you guys get started?